Right, well, welcome everybody to another online meeting of our Neighbouring Astronomical Society. Nice to see you all joining us again. Hope everyone's keeping safe, well, and fingers crossed COVID free. This evening's speaker is Alan Fitsimmons, who's a Professor of Astronomy at Queen's University Belfast. And from what I understand, from what I've been reading, Alan's basically interested with comets, asteroids, and near-Earth objects. And he's been involved in a number of bits of research, as I can understand. I'll pass it back to Les to set everything up for Alan. Just a reminder that after we've had a presentation from Alan, we will be keeping online for a period of time. So if anybody has any items they want to discuss, just a general astro chit-chat, and a bit of socialising, which we've been obviously lax in the last year because we've not been able to meet together in person. So without further ado, thanks very much, Les, and thank you, Alan.
Brilliant, thanks, Les. Alan, I've already passed you the presenter rights.
Thank you.
So why don't I hand over to you, and you can tell us all about near Earth objects and potentially how to avoid them, or at least how to know where they are.
Yes, certainly. Let me just try sharing my screen then. Super. Now, can you see my first slide?
It looks a little bit, it's got bigger. That's it. Perfect.
Okay, super. Please shout out if there does seem to be a problem. And WebEx is asking me, is it okay? And I'm saying yes. That's a nice bit to ask. So anyway, I'd like to start by thanking you for inviting me to talk to you. It's nice that I can do so, of course, because in normal circumstances, it's a little difficult for me to give talks to societies and astronomy clubs in England, living in and working in Northern Ireland as I do. I just wish I had this opportunity for different reasons. But I do hope you enjoy, or at least find interesting, what I tell you about this evening. And I'm sure many of you have some knowledge or some idea about the threats and the opportunities posed by near-Earth asteroids and indeed near-Earth objects. But I thought it might be nice to give you an insider's view this evening, as I've been working in this field for probably a little over 20 years now. And it is quite fascinating. But I'll start at the beginning, and I'm not going to assume that everybody is highly experienced in and knows a lot about astronomy and the solar system. So, there we go. That worked. That's good. So here's a graphic which basically lays out, not to scale, where everything is in the solar system. We have the sun, of course, on the left-hand side at the center of our solar system. And then we have the inner planets, Mercury, Venus, Earth, and Mars. We have our two gas giants, Jupiter and Saturn, and then our two ice giants, Uranus and Neptune. Those are the 8 planets orbiting the sun. Now, in between Mars and Jupiter, we have a belt of rocky objects that we call asteroids. And up until about 1992, that was basically it. Apart from these weird things that seem to have orbits that cross the orbits or the paths of the planets, called comets. Now, in 1992, another belt of objects was started, or at least started to be discovered, called the Kuiper belt. And this is the belt of icy objects outside the planet Neptune, from which about half of the comets that we observe actually come from. So we have the 8 planets in our solar system, but then we have this multitude of smaller objects that also orbit the sun. And the easiest way to remember the difference between asteroids and comets is that on the left-hand side, I've got a nice spacecraft image of an asteroid. This is actually asteroid Ida from the Galileo spacecraft, taken as it passed through the main asteroid belt between the orbits of Mars and Jupiter. And asteroids are rocky bodies. Most of them are between about 100 meters across and 100 kilometers across. We have some even larger in the asteroid belt, including the largest asteroid Ceres, which is 933 kilometers in diameter. And then we can go down below 100 meters, although objects that small generally we can't see in the asteroid belt from Earth, even with our largest telescopes. But we can see asteroids that size if they come closer to our planet. On the right-hand side here, we have a typical comet, or I'd like to say it's a typical comet. We don't really know for sure because comets can be hard to study. This, of course, is a beautiful image of the nucleus of comet 67P, Churyumov-Gerasimenko, as imaged by the ESA Rosetta mission, which successfully orbited the comet between the years 2014 and 2016, and told us, and is still telling us, a huge amount about these bodies. But these are, as I've labeled here, mostly icy bodies. They're similar in size to small asteroids, mostly between 1 and 10 kilometers across. Again, we know of larger objects that are out there. We don't know of too many smaller ones, interestingly. There seems to be a dearth of small comets below a kilometer across, and we think part of this is because of their fragile, icy nature, in that if they get too close to the sun where we could see them, then they would break up or vaporize. Now, you may have heard that occasionally these objects hit our planet, asteroids and comets, and that is absolutely true. It's a natural process. It is just a natural, let me start again. It's a natural process that's caused by the dynamics in our solar system. Asteroids and comets have orbits that can change and evolve, and occasionally one of those objects will be in a path which crosses the path of the Earth, the orbit of the Earth. Now, even then, it's not guaranteed they will collide. What has to happen is that both the orbits must cross, then both the asteroid or comet and the Earth have to be in the same place at the same time, and that's a collision. But they do occur, and they happen more frequently than you might expect, at least for small asteroids. This is a map of all the large fireballs detected in our atmosphere, as the figure says, from the start or near the start of the year 1988 up until New Year just passed. And each of these circles indicates where a large bright fireball was detected, not from the ground. This is data from US Department of Defense satellite network, which is actually up there to try and detect nuclear explosions by rogue states, nuclear weapons tests. But it turns out they're very, very good at seeing bright flashes in the Earth's atmosphere. That's what they were designed for. And so they actually give us a very good idea of how our planet is constantly peppered by small asteroids. And here we're talking objects between perhaps a meter across and a few meters across, by and large. We don't see those on the ground normally. Most of them explode high up in the atmosphere, and if one occurs tonight over the other side of the world, we would know about it. Although if it did occur above us in the UK, we would see a bright flash in the sky as this object entered the atmosphere at high velocity, burned up, and probably exploded by disintegrating it almost instantaneously, as I said, at high velocity. Now, if we have a larger object, then a larger object can penetrate further through the atmosphere and may even get closer to the ground. And about 7 or actually almost 8 years ago now, I was called up by the BBC to ask about this, because at that time, we were having a close flyby of a previously discovered asteroid. In fact, it had been an asteroid that had been discovered in the spring of 2012 that could pass close to our planet. In fact, it was a near-Earth asteroid called 2012 DA14. And this is a screenshot from the website when it appeared. And in fact, they were asking me, is it possible that we might get hit in the future? And I was saying, well, we're slowly building up our catalogue of existing near-Earth asteroids. Every time we find an asteroid that can pass close to our planet, we catalogue its orbit and figure out if it's going to come near us. But then they said, yeah, I ask, couldn't we be taken by surprise in the middle of the night by a completely devastating, completely unknown asteroid? And I said, yes, we could. And in fact, the most likely scenario at the moment is that the next impact will occur with very little warning. Well, that story appeared online at 2:55 in the morning on the 15th of February. 25 minutes later, an 18-meter previously unknown asteroid entered the Earth's atmosphere near the Russian city of Chelyabinsk. Even though it is 18 meters across, it did not reach the ground. It exploded at about 20-30 kilometers altitude. However, the shockwave from that explosion, when it reached the ground, injured 1,600 people. Luckily, nobody was killed, but just the shockwave of that tremendous explosion in our atmosphere was enough to do significant damage across that city. Now, fireballs like this are worrisome. Even more worrisome would be a larger asteroid which reached the ground. And I've got a piece of such an asteroid here. This is a piece of an asteroid that hit the Earth 49,000 years ago. And this is just a small fragment of it that managed to survive that passage through to the ground. And when it hit the ground, it made this. Meteor crater, Arizona. Now, none of us can travel much these days, but if you ever get the chance to travel to Arizona, most people make a beeline for the south rim of the Grand Canyon. But if you're traveling there from Phoenix or Flagstaff, then just before you get there, if you turn right on the highway, you'll end up here, where, as I said, 49,000 years ago, a small asteroid, probably only about 50 meters across, entered our atmosphere and made this crater over a kilometer across. Now, in this photograph that I took, it's really hard to get the scale of this crater. Perhaps if I show you this, it might give you a little bit more of an idea, because in this image, there is a group of friends of mine that were at a conference actually going down into the crater itself. Now, if you look carefully, you might be able to see them in the middle of the picture, but just over to the right. And if you can't make them out, let's zoom up a little. There. Now you can see them, in fact, down here to the lower left, and I've placed the image there so you can see the edge of the escarpments on the crater rim on the right-hand side. This is a huge structure, and it really is worth going to visit if you do get a chance. And it is a great crater. It's very well preserved, but it's only one of over 100 craters that we have managed to catalogue across the surface of the Earth. And this is an astronomical society. You probably realise that that's not all the impact sites that there have ever been. We live on a planet that undergoes continuous erosion because of weather, because of oceans, tides, even because of plate tectonics. If you would like to have some idea of how many asteroids and comets have hit us over the history of the Earth, go out and take a look at the moon. The moon preserves a record of the impact rate in our part of the solar system since the formation of the Earth-Moon system. Our planet would look like the moon if it was not for plate tectonics and erosion, together, of course, with our atmosphere. So clearly, we have been hit quite a lot by asteroids and comets in the past. We're going to be hit again in the future. As I said, it's a natural process. That is, we're going to be hit unless we do something about it. Why should we worry about getting hit? I mean, these are where all the craters are. If we can spot an asteroid or comet that's coming towards us, surely we just need to step away from the impact site and we'll be okay. Well, even for a small impact, there are a number of different physical effects that you need to worry about. So first of all, you've got the asteroid itself or the comet itself. You don't want to be standing underneath it when it hits you, given that the average impact velocity of an asteroid or comet is about 17 kilometers per second, roughly 10 miles a second. You don't want to be there. But then when it hits, most of that object is immediately vaporized in a fireball. And so if you're standing to one side, great. Now you're toasted and you are vaporized by that fireball. That impact will also send shock waves through the ground, giving you earthquakes. If you hit the ocean, you'll probably get through the ocean and you'll hit the ocean floor and still have earthquakes, but now you've also got a tidal wave. In the atmosphere, you've got a shock wave traveling outwards at the speed of sound, or perhaps even faster. It could be supersonic initially, which again means that you're going to have huge amounts of disruption due to this shock wave coming through the atmosphere. And finally, if this object reached the ground, you will excavate a huge amount of the Earth's crust. That's where the stuff that was once in the crater goes. It goes back up into the atmosphere, generally into the stratosphere. Most of it does not escape into space. Most of it will fall back down again, and some of it will fall very close by or at a reasonable distance from the crater, but the rest of it will stay suspended in the stratosphere. And that will then give you problems in terms of, well, we're used to the term global warming at the moment. This will give you instantaneous global cooling, what we used to call akin to a nuclear winter if we were to undergo a nuclear war. And we can play the game. We now have the ability to model and simulate impacts like this and see what kind of effect they would have. So here's a game. This is a paper published by Klaus Rumpf and his colleagues just 3 or 4 years ago, where they took Europe and they took where everybody's living on Europe, and they took the geography of Europe and peppered Europe randomly with different asteroids of different size coming in at different directions. And you can do this in a computer simulation, and for each of these impacts, one can calculate how many people die. And when you do that enough times with enough random impacts, one gets a kind of an average effect curve of what happens with an asteroid impact. And this is a curve published not from that paper, but from one that was slightly earlier, about 10 years ago now. So on the bottom axis, going on the horizontal axis, we have the diameter of the asteroid going from just a few tens of meters through to 0.1 kilometers, 100 meters, to 1 kilometer to 10 kilometers. On the vertical axis, we have on average the number of deaths we would expect to occur. And the number of deaths you'll get, well, certainly that one big discriminant is whether or not for small asteroids, whether it's a land impact or an ocean impact. But if you combine all of these different impacts, what one ends up with is this red line. And that red line shows that even for small impacts of asteroids, say 100 meters across or so, then on average, one might expect 100,000 people to die. As one goes up towards 1 kilometer, you pass through the million fatality mark and even higher. Then once you get around about 1 kilometer diameter, there's a step change, because all of the calculations show that once you have an asteroid 1 kilometer across or larger hitting the Earth, you change from local or regional effects to global effects. Basically, you end up with enough material in the upper stratosphere that you introduce global cooling, which affects crop production and food production, which then has a knock-on effect of food shortages and unfortunately starvation. And so once you get up to asteroids more than 1 kilometer across, you are talking about a number of deaths, unfortunately not in the millions, but in the billions. So we want to stop this, or at least we want to make sure it's not going to happen in the near future. Now, you might want it not to happen in the near future. Surprisingly, opinion might be divided. About a year ago, actually it was in February last year, looking ahead to the US election, Time magazine held a survey, and they came up with this quite surprising result from this survey. Thankfully, we haven't had a large asteroid impact, and I'll leave you to express your own personal views about the outcome of the US election. But politics aside, the amazing thing about an asteroid impact or comet impact is that we know they happen, and it's a form of a natural disaster, just as we have earthquakes and tidal waves and volcanoes. Except we now, as a species, have the possibility to prevent an impact, or at least give ourselves warning. Even hurricanes, you may only have a few days warning. Volcanoes, or you're lucky if you've got a few days warning. Earthquakes, generally you have no warning whatsoever. But we can at least give warning and theoretically, at least at the moment, prevent an impact. So here's how we need to tackle the near-Earth object threat. It's the 3-step process. First, you need to find the near-Earth objects and measure from your data where they are going. Find out, are we going to be hit in the near future? Secondly, you need to measure their properties. If one of these objects does hit, as they have done in the past, what happens? How can we make more accurate these threat curves that I've just shown you? And then finally, of course, can we develop a technology to prevent an impact, or at least mitigate its effects? Well, looking at our ability to find these objects, it's grown tremendously over the past 30 years. This is a typical map we might have of the solar system these days. I notice this is about 1.5 years old now, my apologies. But this is a map showing in the center, we have a little yellow star, that's where the sun is. And then we have the orbits of Mercury, Venus, Earth, and Mars. Then we have a gap, then we have the orbit in blue of the planet Jupiter. Now, each of these dots on this map is the position of an asteroid or comet or some other kind of perhaps in between object that we have discovered at that point. The green mass of material that you can see, for example, between the orbits of Mars and Jupiter, Those are the main belt asteroids that live their lives between Mars and Jupiter at the moment and aren't going anywhere particularly soon. The red dots, however, are the positions of objects that can come in closer than the orbit of Mars and approach the orbit of the Earth. These are the near-Earth objects. And if we zoom up there, one can see that, first of all, it looks quite a crowded place, the inner solar system. But this is a very deceptive plot because we're restricted to using so many pixels in our digital images and so on. It looks as if asteroids should be running into us every day. But that's a false impression given by this plot, because we know that doesn't happen, because we don't often go out in the night sky to do our astronomy and see a big fireball or even an asteroid impact. In fact, the rate of asteroid impacts is pretty small. And we know this from making this catalogue. These catalogues are enhanced by telescopes such as these. These just happen to be the two surveys that I've worked in my career to date. On the left, we have the Pan-STARRS 1, and in fact, not shown here is its sister telescope Pan-STARRS 2 on the island of Maui in the Hawaiian Islands. These are currently the largest survey telescopes dedicated to searching for near-Earth objects, operational each night. On the right, we have the Atlas survey, two twin smaller telescopes. The Pan-STARRS telescopes are 1.8 meters in diameter. Atlas is only 0.5 meter in diameter. But again, working each night, looking for new near-Earth objects. Oops. Actually, I meant to have these captions up already. I apologize. So Pan-STARRS, as I said, it's twin 1.8 meter telescopes. Their cameras have 1.4 billion pixels. So if you want to use it, if we all use digital cameras now, so that's 1,400 megapixels each. In a single 30-second exposure, they get down to magnitude 21.5, maybe 22 on very good conditions, and they survey 3,000 square degrees per night. Atlas, it's a smaller telescope. They have cameras that hold it's 10,000 by 10,000 pixels, so they're just 100 megapixels. Because they're only 0.5 meter telescopes, they only go down to magnitude 19.5 in a typical 30-second exposure. But between them, they survey 13,000 square degrees per night, half of the night sky that can be seen from Hawaii. So whilst Pan-STARRS is sensitive and can see fainter near-Earth objects, which might be smaller objects close by or larger objects further away, Atlas is very good at detecting objects very rapidly when they're close to us. And Atlas is more of an early warning system for objects that are coming very close to us right now. And we find these objects by this kind of method, by simply blinking images. This is an image actually of one of the last near-Earth objects I found with Atlas, which on Saturday this week, this is 2021 BC. These are the discovery images. And what we can see is a small fraction of one of the fields that was imaged by Atlas in this part of the sky. And we can see that the stars, background stars and galaxies pretty much stay where they are. But highlighted by the cross, there is a small moving dot of light. And in fact, that the rate of motion, the direction of the motion of that dot of light immediately told us that this was a near-Earth object. And because it wasn't already in the catalogue, we knew it was a new object. And this was at magnitude 18.8, as I said, on Saturday. Within a couple of days, actually within less than 48 hours, more observations had tied down its orbit. We know this asteroid is about 70 meters across. Actually, on Monday was its closest approach. It approached us about 10 times the distance of the moon. When we look at the orbit of that asteroid and we and we see how close theoretically it could come to us, it can't hit us at the moment. The closest it can come is 2 lunar distances. But there we go. We've got another near-Earth asteroid. It's now in the catalogue. We know where it's going in the future. Now, to know where it's going in the future, as I've said, we've now got an orbit for this object. And in fact, here's the orbit of that asteroid that we only discovered on Saturday. And in fact, this is, so we've got the sun in the center, we've got the orbits of the planets, and the relatively oval path in white is the orbit of the asteroid. And we've even got on here the position of the asteroid down towards the bottom right. And you can see the Earth nearby where we first discovered it. One has to be careful with orbits like this, because to us, this looks like everything's in a 2-dimensional plane. That's not the case in this for this asteroid. This asteroid's orbit is tilted relative to the plane of the orbits of the planets. And if we look on the side, towards the side, we can actually see that this asteroid can be significantly above the Earth's orbit and below the Earth's orbit at different parts in its own trajectory around the sun. But nevertheless, we now have this orbit calculated, and we can show that it's not going to cause us a threat in the near future. Sarah said my date says 16th of January 2020. I'm sorry. Yes, that should be 2021. Thank you, Sarah. Always check my figures, by the way. But yes, it's actually 2021 BC. It should be 2020. It was discovered. I discovered it on this Saturday. But looks like, as usual, I'm living in the past. Thank you, Sarah. Okay. So important thing is we have a catalogue, and we have 2 parallel but independent systems continuously performing risk assessment of newly discovered and previously discovered near-Earth objects. We have one run by the European Space Agency out in Italy, and this is the Space Situational Awareness page. We have one run by NASA at the Jet Propulsion Laboratory in Pasadena. And both of these systems run simultaneously, but independently, actually using completely independent codes, computer software, and actually even independent mathematical algorithms for assessing the possible impact risk of asteroids in the future. So if you ever want to find what the current risk is from near-Earth asteroids, you can go to these pages. They're completely public, and you'll be able to see what probability there is of any asteroid that we have discovered hitting us in the next 100 or 200 years. Let me give you a bit of a spoiler at the moment. There's nothing on these pages that is definitely going to hit us, okay? And in fact, as of today, we have found 25,010 near-Earth objects. We passed the 25,000 mark in the last 24 hours. Wasn't that great? That was really, really good. Now, saying that, we have occasionally found asteroids on an impact trajectory that are definitely going to hit us. We've found 4 so far, but all of these have been small asteroids, somewhere between 2 and 4 meters across. And these are small objects that exploded harmlessly in the upper atmosphere. The important thing is that this system is there for when we find a larger asteroid that looks as if it could hit us in the future. Now, the interesting thing is that these surveys not only tell us whether or not we're going to be hit in the next century or so, we can also use the data to find out how many there are, the ones we've found, but also the ones we haven't found. Let me just go here. And so here we've got a plot, a recent plot from Mikhail Granvik and his colleagues, published because must remember it's January now, 3 years ago, of the number of asteroids there are versus size. Now, This is in what we call absolute magnitudes. But basically, as we go along with the x-axis from left to right, you're going to smaller sizes. And as you go to smaller sizes, the number of asteroids you have bigger than that size increases. And you can see, if you just look at the colored lines, you can see we're doing pretty well. These are all independent estimates of how many objects there really are. And they all pretty much agree until you get to actually relatively small sizes, less than 100 meters across. The black line on this plot shows how many we've found at that point 2 or 3 years ago. So one nice thing is that we can first of all calculate the average impact rate. On average, our 10-kilometer diameter asteroid hits us once every 100 million years from this size distribution. A 1-kilometer asteroid, that threshold for global consequences for an asteroid impact, only hits us still once every roughly 750,000 years on average. And then if we go down to 100-meter asteroids, probably about one every 15,000 years or so on. So all of these numbers show that this is pretty rare, except it's a random process. And sure, we've got all the asteroids we've found so far are not going to hit us in the next 100 years. But that doesn't mean that the next one we find tomorrow night isn't going to be on an impact trajectory. We won't know until we've played asteroidal Pokemon, and because we've got to catch them all, or at least as many as possible. Put another way, here's a plot. I've taken that data, and on the left-hand side, I've compared actually as of Christmas this year. In black, I've got the total number of asteroids found bigger than a certain diameter versus our theoretical red line, which is how many we think actually exist in total. Then on the right-hand side, I've converted that to a percentage completeness plot, which is what fraction of the asteroids at a certain size have we found. Now, I know there's a kind of a triangular dip above 1 kilometer there, but that's just a problem based on my actual code that I need to fix. Actually, we have found almost all asteroids 1 kilometer across or larger that are near Earth asteroids. There's probably a handful left, maybe 10, maybe even 20, but we've found about 950 so far. And that we've really kind of retired the risk. But as we go to smaller sizes, you can see the completeness, that red line goes from 100% down through 80%, through 60%, through 40%, until we get to asteroids about 200 meters across. We've hardly found any of them. We've found just a very small fraction of that population. So there's still a lot of asteroids to be found, and we can still be hit by them. To know what's going to happen, we need to investigate their properties. And there's a whole area of research into near-Earth asteroids that I can't go into during this talk, but I'll highlight a couple of really surprising results that people often don't know outside this field. First of all, we're used to thinking of asteroids as solid lumps of rock because that's what they look like in science fiction films. Actually, most asteroids between 200 meters and across and 10 kilometers across are not solid. They're rubble piles. They're basically self-gravitating piles of broken bits of asteroids that were created in collisions in the asteroid belt millions of years ago. And this is a beautiful example here on the left of asteroid Itokawa, 0.5 kilometer long, as imaged by the first Japanese Hayabusa mission. Not only that, 15% of the time when we find a near-Earth asteroid is not just one. 15% of near-Earth asteroids are binary objects, 2 asteroids, generally a larger asteroid with a significantly smaller asteroid orbiting it as a kind of almost like a mini Earth-Moon system. So that means you've got to remember that 15% of the time, when you're going to be hit by an asteroid, you're going to be hit by two. So, oops, there we go. That's better. Now, we're continuing these missions all the time. So you may be aware that we've just had two highly successful rendezvous missions with the near-Earth asteroids. On the left, we've got asteroid Ryugu, which was visited by the Japanese Hayabusa 2 spacecraft, and has since sampled 2 pits of that surface and brought it back to Earth. We have also had the NASA OSIRIS-REx spacecraft at the slightly smaller near-Earth asteroid Bennu, and that will also bring samples back to Earth, but not until the year 2023. So we're learning more about the physical properties of objects all this time, and we can build the properties we measure about their density, about their composition, and so on, into our impact models. So here we've got a still frame from a supercomputer simulation by Mark Bosler and colleagues of what happened during the Tunguska impact, when a 50-meter asteroid, we believe, entered the Earth's atmosphere in 1908, again in Siberia, just like Chelyabinsk, or at least in Russia. But here there wasn't, as far as we know, anybody injured. Although I believe a herdsman was knocked off his feet by the shockwave. And again, by taking that information we get from spacecraft and telescopic observations and building it into our models, we can understand better what happens during an impact. So we've got a great deal of understanding there, but when it comes down to it, again, what we would like to do, if there is going to be an impact, is prevent it. And you can't prevent it when the asteroid has entered the atmosphere. It's too late. Remember, these objects are traveling at 17 kilometers per second on average, 10 miles a second. It's not like the science fiction movies where you've got time to get out of your car, point up, get your camera, take a photo, go, oh, look at this, tweet it or put it on social media. You've got a few seconds between that object entering the atmosphere and the object landing. And then it's game over. So we need to prevent it. Effectively, I'm not sure if your bandwidth is up to this, but the movie is playing. So I didn't know the movie was playing. That's great. So this is the simulation from Mark of the Tunguska impact, or at least one possible simulation, because there are a number of models fit the after effects of that. So effectively, asteroids are nature's way of asking, how's that space program coming along? Because the only way to stop an asteroid hitting us is to meet it out there in space. Now, there are a number of techniques that have been suggested in the past. And in fact, I saw a question flash up on my screen about painting asteroids white. Well, you can, but we cannot predict what's going to happen. There are many possible technological solutions, but there are only 3 that we have the current technology to do. The first on the left is the technique called the gravity tractor. And this is actually the most tricky of these 3 technology solutions. What we're doing here is using Newton's law of gravity as a tow rope. Because if we stop an asteroid, if we stop a spacecraft relative to an asteroid, we know the asteroid's gravity is pulling on that spacecraft and will pull it down onto the asteroid itself. But Newton's laws of physics tell us that the spacecraft is pulling on the asteroid by its own very weak force of gravity. So if we can hover a large spacecraft above a small asteroid and continuously fire the thrusters to maintain the distance between the spacecraft and the asteroid, we can actually move very slowly that small asteroid into a different orbit. And so in years hence, instead of that asteroid hitting the Earth, it sails harmlessly by. Now, as I said, this is the trickiest technique we might come up with at the moment, because we've never tried hovering a spacecraft precisely above a small asteroid for at least a year and probably several years to give it a small nudge and slowly tow it via gravity to a slightly different orbit. But in theory, with our current technology, we could at least attempt it. The middle technique is the kinetic impactor. This is basically cosmic billiards. If you want to move an asteroid into a different orbit, you hit it very hard and very fast with a spacecraft. And conservation of momentum will mean that asteroid gets a small kick in the opposite direction from whence the spacecraft came. And again, that small kick will move that asteroid into a different orbit, and you will hopefully avoid an impact on the Earth. The final technique we have on the right is what we call blast deflection, or if you like, it's the Bruce Willis method, in that we take a large explosive device, probably nuclear, and explode it just above the surface of the asteroid. We don't try to destroy the asteroid. That's probably not possible. But we explode the device, the nuclear device, above the surface of the asteroid. The blast vaporizes the surface of the asteroid. That vaporized asteroid goes one way, and again, conservation of momentum means the asteroid goes the other way. And so once again, here we have moved an asteroid into a different orbit. Now, that also is definitely possible with current technology. Our concern is breaking the nuclear test ban treaty in outer space, because the last thing we want to do is set a precedent for various nations around the world to put nuclear weapons into space. So what we're going to do is think about this, because it turns out that the technique that's going to be most effective will depend on both the size of the asteroid and how much warning time you've got. When you've discovered this asteroid from your telescopic surveys, how many years in advance of the impact do you find it? Now, if it's a very small asteroid, say 50 meters across or low, the likelihood is we are not going to find this asteroid in any kind of time before it hits. In fact, the likelihood is if the next 50-meter asteroid impact, if it occurs tomorrow or in the next year, if we're lucky, we will see that asteroid at most a few days before impact. So that's why we'd say that any small asteroid, our most likely form of mitigation against the effects of that asteroid impact, is civil defense. We basically evacuate the impact area. A 50-meter asteroid will pack a certain punch. It will devastate. If it was landing on a city like New York or London or Berlin or Dublin, that city is gone after that impact. But we would be able to evacuate at least a large fraction of that population before the impact if we have a few days warning. For an asteroid between 100 meters and maybe 300 or 400 meters in diameter, if we have a lot of warning at the moment with our spacecraft technology, and we're probably talking several decades, then we could try the gravity tractor approach. Because although we think it might work, it's a very slow method of moving an asteroid. If we've got less than 20 years warning, then the likelihood is that we'd use a kinetic impactor, hit it hard and fast with one or maybe more than one spacecraft. Then finally, if you've got an asteroid that's coming towards us a kilometer across or more, the only option is nuclear, we believe. To be sure, we would need to break the test ban treaty with the agreement of the United Nations, and there are United Nations committees set up to consider this, we would have to go for the nuclear option. The interesting thing is that if we put that to one side, and let me go back here, whoops, sorry, the area that we're most concerned about, given that we've actually retired most of the risk from large asteroids, is in this region of about 100 meters to maybe half a kilometer, where the most likely technology we'd use is the kinetic impactor. So we're going to do it. We have funded and are currently building a joint spacecraft project to go and test if we can move an asteroid into a different orbit. Its original name was the Asteroid Impact and Deflection Assessment Project, or AIDA. I'm not sure we're still using that phrase anymore. We've kind of retired it from the official documentation. But what we have in its place are the two spacecraft. NASA DART, currently under construction over in the United States, and the ESA HERA spacecraft, which has just passed its first preliminary design review just before Christmas. We're going to test moving an asteroid on this object, near-Earth asteroid 65803 Didymos. This is again a side-on view of the, oh sorry, there's some extra text there that shouldn't have been there. This is the side-on view of the orbit of Didymos in white compared to the orbits of the inner solar system. And as you can see, the asteroid in its orbit approaches the orbit of the Earth, but passes just outside the orbit of the Earth every time it's closest to the Sun. Now, the cool thing about this asteroid is that it's one of our binaries. Whoops, let me just skip that one. This is a kind of a mock-up I've made of what this system might look like. We haven't visited it yet by spacecraft. All we have are some low-resolution radar images plus images from ground-based telescopes where it's just a dot of light. But what we have is a main body that's about 780 meters in diameter. It has a moon that's about 150 to 180 meters in diameter. And the moon is about 1.2 kilometers from the center of the main asteroid. And our combined DART and HERA mission is going to test kinetic impacts by hitting the moon, not the main asteroid. Why is that? Well, if we look at the rotation of this system, the main asteroid rotates every 2.26 hours. We don't know how quickly the moon spins on its axis. That was named last year, by the way, Dimorphos. Dimorphos. I should pronounce it correctly, Dimorphos. But we believe it probably spins on its axis in the same length of time it takes to orbit the main asteroid, 11.92 hours. And the idea then is that we will hit this asteroid, Dimorphos, the small moon, with a kinetic impactor and change the orbit of that small moon around the larger asteroid. And we will be able to measure the change in orbital period of that moon, and therefore the orbital distance of that moon, by ground-based observations, from both ground-based radar and also by ground-based telescopes looking at the light curve of the moon occulting the primary asteroid. And unfortunately, this means that we have to lose one of our spacecraft, and that is the DART spacecraft. It will launch this summer in 2021. It will impact in late September 2022, but just before impact, will deploy a CubeSat built by the Italian space agency called LisaCube, which will send us back images of the impact of DART on that moon. Then 2 years later, in October 2024, we will launch the European spacecraft Hera, and Hera will rendezvous, not just pass the flyby, but it will rendezvous with the Didymos Dimorphos system at the end of 2026. And it's going there not to show that we can move a small asteroids, because that is what DART will do. But Hera will accurately measure the mass of Dimorphos. It will measure the mass of the moon. So we know the mass of the asteroid that we moved, and we know how effective the kinetic impactor technology is. It will actually be there. The current mission plan is to be there for a year. And if I'm appearing slightly tired, it's because we had another Hera operations meeting starting at 8:30 this morning. So I've been in front of this computer now for almost 12 hours. So I do apologize if I'm slurring my words slightly. But together, importantly, DART and Hera will provide us with our first controlled test of moving a small asteroid, and will also show us how efficiently we can do that. So, in conclusion, the impact risk for asteroids more than 100 meters is well understood, in that we know roughly how often they occur on average, and we've now got a good technology and capabilities of finding them and calculating the threat from individual asteroids. And indeed, the near-Earth object surveys are doing an excellent job, but there are many left to find. It's clear, particularly when we get down to 300, 200-meter asteroids, which will not cause global devastation, but could certainly cause devastation over a region the size of a small country. There are many left to find. Our knowledge of near-Earth object properties and impact consequences is well developed as well. We now have very good models of what happens when asteroids enter the atmosphere, and what the likely consequences are of impacts. However, we do have to be careful, because these are simulations, and for a very good reason. We don't want to do that experiment. We don't want to let an asteroid land and find out if our calculations matched what really happened. But if we don't want to do that, then we do have to test our potential technology for moving asteroids and changing their orbits so they don't hit us. And that means we're happy to say that we're about to perform the first test of asteroid deflection technology. So all of this, I think, is pretty upbeat, but I'll remind you that we still have a lot to find. So just as I said 8 years ago to the BBC, the next impact by a small asteroid, at least, can still occur without warning. Thank you very much for listening.
Absolutely brilliant talk, Alan. Thank you very much for taking us through not only your work, but I know the work of many others around the globe. And I think what we need to do first of all, I'm going to unmute everybody. Make sure you're all unmuted, and invite everybody to thank Alan in our normal way. In these days of back-to-back Zoom meetings and so on, that's probably about as interactive that we're going to get. But no, absolutely fascinating talk, and I think you touched on quite a few different sort of aspects there, from discovery and from learning about the impact, and also mitigation. And it sort of occurred to me near the end of your talk that when you were sort of summing up there, you know, we're trying to identify and analyze asteroid sort of characteristics, and if I may say DNA, still working on the vaccinations, but it looks like it's all going to be about social distancing.
Yes.
Brilliant. Yes. So if you're okay for a few minutes, we've got a few questions that have come up. So I'll just sort of try and rattle down them fairly quickly. I think there was this one was from Clive, probably around where you were doing the simulation. I think there was a simulation of impact sites across Europe and so on. And the question is, why are there apparent clusters of impact sites?
There weren't. It's random. I mean, honestly, the interesting thing, it's a good question because, the human eye is very good at seeking patterns and so on. But no, those sites were completely random across Europe. It's interesting question, though, because it actually shows you how you've got to be careful when you actually look at something. Now, funnily enough, of course, we use a lot of software in our near-Earth object searches. So all of our discoveries these days of near-Earth objects are done using computer software, in that the software is automatically finding new moving objects. But in that case, we don't trust the software 100%. So every time we find the software reports what it thinks is a new near-Earth object, we eyeball it. We do not report any new near-Earth objects without us first inspecting the data by eye. And it's not so bad. You get used to it. It takes a while, but it's good because it maintains the quality in the system. So it's interesting that actually in part of this program, we're not at the case yet where the artificial intelligences have taken over. Let me put it that way.
But I guess equally, if you're eyeballing, if you're eyeballing by eye, that's not something that you're sort of putting out to citizen science to do either.
No. No, although I did see, I think, a comment coming up in the chat about follow-up observations. And one thing that didn't come out in my talk, unfortunately, but it should have been there, is that although the surveys have to be done by professional telescopes, because you just need you need both the acreage, the size of the telescope, and you need the sky coverage, and you need the rapidity. Because if you've got something coming in the next 24 hours or so, you can't wait very long to report it, and so we need a professional level there. But once it is a suspected near-Earth object, then they are announcing publicly accessible pages called near-Earth object confirmation pages, and many of the follow-up observations that allow the determination of the orbit, and even at the end just confirming that it's real, because sometimes the professional observatories get things wrong. A lot of that follow-up is done by amateur astronomers. Now, I use the term amateur. As far as I'm concerned, they're doing exactly the same level of work as the professional astronomers. It's just that they have more time and they have the ability to do that follow-up work. And that's going to be the situation for the foreseeable future, at least in the Northern Hemisphere, anyway.
Absolutely. And I am actually pleased to say one of our watchers via live stream on YouTube is a friend called Guy Wells, who is actually one of those very guys who has got his own designated observatory, North Holt Branch Observatory.
Yes.
So he's actually reporting on those. Yep.
Yeah, absolutely. I'm familiar with Guy's work. He followed up a few of my objects from time to time, and I'm very grateful about that, as is the rest of the NEO community. And it really is a community. It's just a shame that whenever we have our international conferences every 2 years, we can't have more of a representation from the amateur community there, because they really do a tremendous job in assisting professionals. I think this is one of the real instances where amateur scientists, in the sense that amateur because they're not being paid to do it, are a vital part of the total scientific process. I think it's fantastic.
Great. Okay. Let's work through the questions. So, given the chart shows the size of impact of the object versus fatalities, is there a sort of an overall size priority or focus for the surveys, or is it about just getting everything? And I think it was the latter. I think it's what you said.
That's a good question. It's basically get anything that's moving, but over time, it's as telescopes have got bigger, we've been able to see fainter objects, though therefore smaller objects as well. The first generation of sky surveys, going back to even the shoemakers using the Schmidt telescopes, the Palomar Schmidt, back in the 70s and 80s. And then the projects Linear and Spacewatch in the 80s going into the early 90s. They were relatively small telescopes, and they actually did a good job of mopping up a lot of the big asteroids, the global effect objects, the 1 kilometer asteroids. And that's why at this stage, really, we're pretty sure that most of that risk from the big near-Earth asteroids has been retired, in that we don't need to, but some of them might hit us in like 500,000 years, in which case, absolutely fine. I'm going to let the grandkids, or the grandkids of the grandkids of the grandkids, worry about it. I'm okay. I'm going to keep paying into my pension fund. But because of that, we now concentrate on the smaller asteroids. We still would want to find. We know there's a handful, at least, of bigger asteroids out there that we've still got to find, and we're still looking for them, and they'll turn up at some point in the regular surveys. But we concentrate now more on the smaller asteroids because that's where most of the unknown risk is. That's where the objects are that we haven't found yet, and that's those size ranges.
Okay, great, thanks. Question from Andrew. I think it was when you were talking about the Pan-STAR survey. You're saying, do you use the Astrometrica software? Can't quite read the rest of the question.
Okay, well, maybe I could find it in the chat, but I'm familiar with Astrometrica, and it's really great software, but no. No, it is really good, but there's a few problems with Astrometrica, one of which it runs on Windows, and that would be a poor choice. So basically, we run bespoke software. All the Zenit servers run bespoke software because this has to be done accurately, and it has to be done fast, and it has to be done dependently. And so we run our own basic software. And it is pretty good. Astrometrica is very good as well, but we wouldn't use Astrometrica to process 100 megapixel images coming in every minute, and that's just for Atlas. If you've got 1400 megapixels coming in every minute from two surveys, then to Pan-STAR telescopes, that won't do. And now, of course, coming up online, we have the Vera C. Rubin Observatory, which I took a look at the webcam, and it's coming on great. It will be on Sky in about 2 years. 3.6 gigapixels, I believe that is. It will, in 30 seconds, it will image down to 24th magnitude. It's an 8-meter telescope, and it will cover the entire sky as seen from Chile every 3 nights. Now, that's got to cause us a bit of a problem. The only telescope able to follow up most of those objects is the Vera C. Rubin Observatory. So its survey is being designed to do its own follow-up because, unfortunately, although we'd all like to be able to image 24th magnitude asteroids from our back garden, not many of us can. But of course, it's in Chile, which means that the Northern Hemisphere surveys, Pan-STARRS and Atlas, we still project to be continuing, at least in the first few years. And that's why that follow-up by the amateur astronomy community is still going to be desperately needed.
Right. Okay. Is there anything that predisposes some asteroids to become NEOs, whereas others are not? That's from Magda.
Okay. Yes, but it's primarily based on where they start from. because we now, well, something I didn't have time to go into in this talk is our growth in our understanding over the past 20 years of how asteroids get from being in the main asteroid belt to being near Earth objects. And there's a complex interplay of gravitational forces and thermal forces, strangely enough, that act to move objects from the asteroid belt into near Earth space. But saying that, so they certainly more asteroids come from certain regions of the asteroid belt than other regions, and that's one thing that would dictate if an asteroid can become a near Earth asteroid or not. But even then, you can't predict unless you actually watch an asteroid out there in the main belt for a few 100 million years and see where it's going.
Okay, and sort of linked in with sort of tracking these. If one's approaching Earth directly head on, and I guess actually as the Earth's orbiting, that's in an arc anyway. But if it was directly head on, would it appear stationary? But I guess it would do for a moment.
Yeah, absolutely. And that's a good question, because I think we're all aware that sometimes you can get head-on meteors, can't you? Where you're looking up towards the radiant of a meteor shower, and if you're lucky, I'm not sure if it's lucky. If you're lucky, you see one heading straight towards you. Yeah, maybe it's not lucky. But for near-Earth objects, they can appear to be moving relatively slowly across the sky if we're kind of running into them, if you like, or they're coming towards us this way. But it won't be exactly stationary. There will always be some motion over a period of at least an hour or so. If nothing else, think about it this way: even if it was exactly in the Earth's orbit, it was coming up directly above us, we're on a spinning Earth. So we're going to be, as the Earth rotates, we're going to see it from one side and then the other. So we'll see the asteroid wobble. And indeed, when we have on our software, where we're not only measuring these near-Earth or potential new near-Earth objects, but we're flagging them up, it actually takes all of that into account. So we have all kinds of figures and plots which tell us the likelihood of this object, if it is real, being a new near-Earth asteroid or not.
Okay, excellent. Just conscious of the time, Alan, so perhaps we'll take one final question, which is perhaps the future of observatories. And George asks, would it be considered if there are a number of observatories on the moon in years to come, and could they serve any practical purpose?
Observatories on the moon would, because of one very good reason. All of our detection telescopes, all of our near-Earth object survey telescopes work at night. We did not see the Chelyabinsk impactor coming in February 2013 because it came in from the direction of the sun. And of course, optical telescopes can't work during the daytime. But if you had a telescope not on Earth, then you can actually look pretty close to the sun if you baffle it well enough and you're very careful about stray light. And indeed, we've known for several years, actually probably a couple of decades from simulations, that if we really wanted to quickly catalogue everything that could hit us, or down to a certain size limit, the best place for a telescope is not on the Earth. Actually, it's not really on the moon either. It would be in an orbit between us and the sun, looking outwards, because then you can spot everything. And this has been proposed a few times. It's never quite worked, and actually at the moment, there's nothing quite on the cards to do it in terms of being interior to the Earth's atmosphere. But there's a project at NASA called currently called the Near-Earth Object Survey Mission, and this would be an infrared survey telescope. The advantage of having an infrared telescope is that not only do you detect the asteroids just as well as you can in the optical, but you also get the size immediately. When we use optical light, there's uncertainty about exactly how big an asteroid is, and if you observe it in the infrared, you can make that measurement pretty directly. But that is still kind of in limbo. It's been in limbo for several years now. There's a trickle of funding into it, but that trickle has never developed into a full-blown development of that space mission. Saying that, it's based on the NEOWISE telescope, or it will be a very much improved version of the NEOWISE mission. And of course, hopefully some of you saw Comet NEOWISE earlier this year in the evening sky, and NEOWISE is still going well. So at least those scientists, those project astronomers who are involved all through this NEO-SM are also involved in NEOWISE, and they've got something to keep them busy while they're waiting for this funding to appear.
Brilliant, brilliant. Well, Alan, thanks once again for such an interesting, fascinating, and sort of slightly wary. But don't panic, guys. You know, it could all be over tomorrow, but perhaps in a few million years. Hopefully, you'll be able to come back to us at some time in the future, Alan, and give us an update. But until that time, thanks very much again, and perhaps we can give Alan another round of applause.
Thank you.
Brilliant. So, Alan, I mean, feel free to stay. We're just going to have a sort of a general chat, but I'm sure after 12 hours of wall-to-wall Zoom and WebEx and whatever, you're probably dying to turn the screen off. But
to be honest, I wouldn't mind if I could actually. But thank you very much for coming along this evening, and thank you very much again for the invitation. Like I said, I hope you enjoyed it, and see you another time. I'm just going to go off downstairs and put something more into my pension fund. That worried.
Brilliant. Thanks, Alan. See you next time.
Thank you. Right. Thank you very much.